All right, thank you. It's great that there's this many people actually interested in graph algorithms. So a little bit about myself. I got my PhD in mathematics from the University of Nebraska about 6 years ago. I studied graph theory. So this is one of my favorite things to talk about. In my downtime, I am a Spark contributor, done some stuff with Spark SQL and some contributions to GraphX as well. I'm currently a principal data engineer at Silicon Valley Data Science. Previously, I was at Walmart as a data scientist and did some large-scale graph algorithm work there. Had a graph that had about 1 billion vertices and 100 billion edges that you needed to get stuff done on. So that's one of those things I'm really interested in. Okay, so a little bit about us. So we're named for Silicon Valley's approach to doing data science, and we happen to be based there. We work in cross-functional teams of software engineers, architects, data scientists, strategists, and designers who specialize in data-driven product development and experimentation. We work in blended teams trained in holistic, strategic, and agile approaches. And we do data strategy, architecture, agile engineering, and agile data science. And if you want to get a copy of these slides or any of the other presentations that we've done at Spark Summit, you can go to our website and sign up, and we'll send it out to you shortly. Okay, so what are we going to talk about today? We're going to first talk about what graph parallel is, some recurring examples that we're going to come back to over and over, and then the two sort of like historical context things that we need to understand GraphX, and that is Prego and Power Graph, and then we'll finally get on to the examples in GraphX. Okay, there's going to be code. Not really any easy way around that. First, we're going to start out with pseudocode, but then in the end, we're going to have Scala code. It's just how it is. Okay, so first, let's talk about the problem space, graph parallel. So this is data parallel for graphs. If you're not familiar with the term data parallel, that's what MapReduce and Spark RDDs and all of these sort of things that do the same thing in parallel to your data on little chunks of your data. Okay, that's the same concept but applied to graphs. This is as opposed to task parallel where you're doing just random separate individual tasks maybe on the whole data set. So it's the way of parallelization. And we need these to be able to do these computations on large graphs in a manner that is easy to express. Okay, so some other properties. They generally are using an entire graph, and this graph is generally going to want to be large. I don't want to really bother with this on smaller graphs. They can be worked on from a local context, that is like from the context of a vertex or an edge in parallel without communication. We'll get to that later. And usually compute some sort of value for every vertex or edge. Okay, so Prego, Power Graph, and GraphX provide graph parallel abstractions. Okay, so we have 3 recurring examples that we're going to come back to for each of these today, and that is connected components, single source, shortest path, and PageRank. So let's talk about what each of these are just so that we're all on a level playing field and we know what we're talking about. So connected components is I want to partition my graph into parts that are connected. That is that I can walk along edges to get from any vertex to any other vertex in each component. So here are the 3 components in this example graph. Of course, I can't really just give groups as an output of a graph algorithm. What I really will get out of it is identifiers where you have the same number if you're in the same group and not if you're not, right? Okay, single source, shortest path. So what this is we start at a given vertex, say A, and we want to find the shortest path to everything else. So for instance, voila. The shortest path from A to D, for instance, is D, along C, then E, then D. But we do that to everything from one single starting point. And the last one, PageRank. So this is the algorithm made famous by Google and models how likely a random surfer is to end up on any given web page. Basically, if you have links from other places that have high PageRank, you get high PageRank. Sort of this recursive definition there. And so like more accurately, without smiley faces, maybe it looks something along those lines. I like the smiley faces, so, okay. All right, so let's talk about the first of our abstractions, Prego. And if it had a motto, it would be, think like a vertex. So Prego came out of Google in 2010. It was actually disclosed in a 2009 blog post, but 2010 is when that paper actually came out. And the model is message passing with super steps. And in each of these super steps, you have a vertex program that runs on each of your vertices and does the following. It processes messages that it got from the previous super step. It updates the vertex's state, and it sends messages that will then be processed in the next super step. And it can also vote to halt, and if everyone decides to halt, everyone agrees, no one sends any more messages, then we terminate and we have the answer. Optionally, there's a message combiner that can combine the messages that are going to the same place together to lower the communication necessary. And there's also other fancy features that only Prego had, like global aggregators, and you could even mutate the graph and other fancy stuff that we don't really care about. All right. Why did Google come up with Prego? Well, because they wanted to run PageRank essentially on a very large-scale graph, that is the internet. And so that's where it came from. Okay, so let's look at what connected components looks like in pseudocode for the Prego abstraction. So we start out with initial vertex state at each vertex of just a unique ID. Everyone starts out with something different. And the vertex program is as follows. It's a function of the messages that it receives. You compute the minimum of the messages. The thing that I've left out here is at the first step, the super step 0, you get no messages. Don't worry about it. The minimum of nothing is just infinity. Okay? If that is less than your current state, update your state. Otherwise, vote to halt. And either way, at the end, we're going to send a message to all of our neighbors of our current state. Okay? And I should mention, generally, connected components is considered on undirected graphs. So this is without any concept of direction to the edges. Okay? And if you wanted to have a combiner for the messages, of course, it would just be the minimum of 2 messages. Okay? All right, so let's do a little animation just so that we're all together on this. So we start out with individual labels, 1 through 8. Let's think about what happens at vertex B. We're just picking one to focus on. Remember, they all run in parallel. Well, not necessarily in parallel, but logically parallel. It's going to get messages from the state of the neighboring vertices. So it's going to get a 1, a 6, and a 7, and itself is an 8. And it's going to update its state based on the minimum of those. It was 1, and that's smaller than its current state, so that's 1. Some of the other vertices also update in that super step. If we run one more iteration, then we get to our final result. Eventually, we get that convergence, which is good. Okay. Single source, shortest path. Just a bit of a tongue twister. Okay, we initially start out with the source vertex has a label of 0. Everything else is just infinity. And on the edges, we have the distance that you travel between those two vertices. This is generally considered for directed graphs, so this is the directed distance between these vertices. And if you don't have an edge in that direction between two vertices, there's no way to get there, basically. You can't traverse, well, directly. So when I refer to the neighborhood here, we're talking about the outgoing edges only. That's why the important thing is. Okay, so the vertex program, again, is a function of the messages. Takes the minimum of all the messages that it gets. If it's less than the current state, it updates it. And then it goes for each of its neighbors, now that it has this new state, and sends off to each of its neighbor its current state plus the value on the edge to that neighbor. So this is basically how the vertex state is the shortest path that it's found so far, and it adds in the length of that edge, and it sends it off to that neighbor. And otherwise, if we didn't make an update, we vote to halt. Okay? I would say note that this vertex program is doing work proportional to the number of outgoing edges. We'll get back to that in a second. Okay, so just as a quick animation, we start out at A. Those are our starting values, 0 at A and infinity elsewhere. In the first super step, we update B and C because we got the shorter paths there. In the next one, we update E and D. We do one more iteration, and D gets updated again with now what is the shortest path. If you ran it again, nothing would change. We've reached convergence. Okay. So PageRank. Once again, we start out with initial vertex state of 1. And here's the vertex program. Now, this one has to guard against the sort of dummy first 0th super step. So if we're not in that first dummy one, we will actually take the sum of the messages and apply our update function, which is just 0.15 plus 0.85 times the sum of our messages. This is sort of the PageRank formula. In general, though, those are not like fixed, but those are essentially the suggested constants from Google. But basically, two things that sum up to 1. And we can just do this for a fixed number of super steps. That works great if you don't want some fancier version of convergence. And in each of those super steps, we're not halting. We're just going to send a message to all of our neighbors of the current state divided by our out degree. That is, we are evenly dividing up our PageRank and sending each little slice of it out to our outgoing neighbors. And otherwise, if we've reached super step 30, we'll just vote to halt. Okay? If you've seen PageRank before, you may be scratching your head and say, I thought we started out with 1 over n or something. There's really 2 different ways of doing it. You can either sum up to n or sum up to 1. They're both the same in the end once you normalize. Don't worry about it. Okay. So let's talk about Paragraph and how it improves on Prego. Okay? And if it had a motto, it would be, think like an edge. Okay, so where did this come from? So the authors noticed that most real-world graphs have highly skewed power law degree distributions, which really challenge some of the assumptions that were made by Prego, which limited its performance and scalability. So specifically think of social networks, where you might have celebrities or someone who has like millions of connections, whereas everyone else probably only has hundreds. So there's this crazy long tail skew at the end that can mess you up. Okay, so what they did was they sort of realized that all of those Prego vertex programs were really doing the same thing, just a bunch of different things. They could really be decomposed mostly into three main things. Gather, apply, scatter, which was their sort of acronym. And really, there was an extra one in there that they didn't mention in their acronym, which was the sum. And that was the sort of the mandatory combiner. But anyways, gather is basically a function of an edge triplet. So basically, given the entire context of an edge, that is each of the vertices on each end of it, along with their values and the value at that edge, we compute a message, okay? And so we are going to apply that gather function for all of either the incoming, outgoing, or both edges incident to a given vertex U. And then we would combine those messages together using a sum into one single message, and then we would apply that single message to our current value to compute the new value. And then the scatter part's a little bit unnecessary, but essentially its job is to update neighboring edge data, activate neighboring things, and optionally, it can do fancy things like send deltas off to be later aggregated as well. Paragraph had some really cool other features in that super steps were optional. It had another mode where it could do asynchronous, either with or without fine-grained locking. So basically, you could have things running continuously with no like sort of arbitrary blocking between steps. And that really helped with some sort of some algorithms, such as graph coloring, that were not very feasible with Prego. Okay. Okay. So let's look at what connected components breaks down into in the Power Graph abstraction. All right, so just like before, we start out with a unique ID, and here's what it looks like. So for gather, this is with respect to you, we look at the other side, what the value is at V, the other side of our edge. And this is for all of our neighbors because this is without direction, because this is connected components. Our sum is just the minimum, and the application is just the minimum of our current state and that sum. And when we scatter things out, this is basically we get to peak at both sides. And I didn't mention, but essentially between each of these steps, there is synchronization, and you can actually look at the values that have changed from that previous sub-step. So minor step, I think, is what they call them. So basically, we peak at the other side of this edge, and if it is bigger, because it's got updated or whatever, then we will go ahead and activate it. Or not because it was activated, but because we changed. Yeah. Anyhow. So single source, shortest path. Same setup as before. The gather method here takes, for all incoming edges, the value of the opposing vertex plus the edge weight. So basically, that's the shortest path we found to that neighbor so far, plus the weight of that edge that is incoming to us. So this is the next candidate shortest path. We combine them together with the minimum, we apply it with the minimum, and to scatter out, one method of doing this is that if we've changed our value, then we activate our outgoing neighbors and say, hey, we've changed, you might want to pull our value in. We've found a shorter path. Okay. PageRank, again, starts with 1 for gathering things. we will take the opposing value divided by its out degree. Really, you can store that as an edge value or use whatever, but that's what it is. The sum's the actual sum, and then the apply is the PageRank formula there. And you can use, for the scatter, you can say, if I've changed sufficiently, like my delta is greater than some epsilon that's tiny, then I will activate my outgoing neighbors. Okay, so great. We have all the historical context we need. We can talk about what GraphX is. So GraphX came out of Berkeley Amp Lab in 2013. It tried to combine the best of both worlds between those two abstractions. So it's a general graph API that's built on top of Spark's RDDs. So essentially, the graph concept there combines together two RDDs. That is a vertex RDD and an edge RDD, and wraps them together and gives that extra graph functionality. So it has an implementation of what I call Prego, with some scare quotes there, where all of the messages are derived from edge triplets, just like PowerGraph. It requires a combiner, just like PowerGraph. But unlike PowerGraph, where it was like explicitly activating neighbors, it has what I would refer to as implicit activation, and that you can set an active direction, and if the vertex on the other side in your active direction has changed, then it will implicitly activate you to run in the next super step. Also, you get run if you get messages. But it also has a lower level aggregate messages building block that's used to implement Prego. I would liken this to a map reduce for graphs, and that's single map reduce type thing. And there's a bunch of normal RDD methods to do other sorts of things. It is unfortunately only Scala. There is no Python wrapper or even Java convenience stuff for it. It's Scala, and that's it. I'm sorry. All right, so with that said, warning, there's Scala code. If you don't like Scala, avert your eyes. Okay, so let's talk about what the signature to Prego in PowerGraph looks like. This is the actual signature from the code. Let me walk through what each of those things mean. So we have an initial message. This is basically what is passed to your vertex program at the beginning, just as sort of your dummy value. It usually does just about nothing. Don't worry about it too much. The maximum number of iterations, basically, this is your failsafe for if I've gone, say, 50 iterations, I want to stop no matter whether or not I still have active vertices or not. An active direction, which is what I've been talking about earlier, which is sort of that implicit activation. Basically, if something's changed in that direction, we will run in the next super step. It's more of an optimization. The default is either, and that'll work just fine for most cases. We're not going to worry about it too much. The vertex program, which is essentially the apply method from PowerGraph. A send messages function, which takes your edge triplet, which is the same sort of context we were talking about in PowerGraph, and gets you an iterator of messages. I will say, though, don't be fooled by that interface. You can only send messages to each side of your edge context. You can't really send messages anywhere else. And a merge message function, which is your combiner or sum. Okay. Great. So what does connected components look like in PowerGraph? Okay, this is a simplified version of the actual implementation that's out there in the GraphX library for connected components. Let's look at each part here. So we start out by taking our graph and essentially setting things up. That is, we are getting a unique value at each of our vertices. How do we do that? Well, we conveniently already have a unique ID for each of the vertices, so we just use that as the value that we're mapping to. Okay, then we run Prego on that setup graph. We have an initial message, which is max value of long. It's a throwaway, just the thing that does nothing. We don't worry about it. Okay, your vertex program takes the minimum, right, just like before. Our send message program, so this is where it's a little bit different from Prego, from PowerGraph, excuse me. With PowerGraph, the sending of the message was within the context of where it was being sent to, okay? And it was called separately for each side. On this, it is called once for the edge entirely. And so basically what it does is it peeks at each side of that edge triplet and sees which side is bigger, and I'm going to send the smaller value to the side that has the bigger value so that we can, eventually can agree on the smallest, okay? And if they're both the same, we don't send any message at all. And of course, the merging, just like before, is the minimum. Okay? Fair enough. Okay, single source, shortest path. So the setup, remember we want to get a 0 for the source and positive infinity everywhere else. So that's what we do. We just map our vertices and find that source ID that we've passed in as a parameter of our function, and we set that one to 0, the other one's not. Okay. Then we run Prego. The initial message is a throwaway again. The vertex program takes the minimum. And the send messages, what it does is it peeks at the destination value, and it sees, is this bigger than the source value plus the weight of the edge? Basically, is there a shorter path to that destination? If there is, we go ahead and send what that sum is to that destination. Otherwise, we do nothing. And merging messages, again, we just use the minimum. Okay. So let's talk about aggregate messages for a second. So this was that other building block. We're going to use this as the implementation of PageRank. Okay, so it has 3 things. It has a send message function, which is very similar to what you had in Prego, although for historical reasons, it has a slightly different signature. Oh well. Merge message function and a triplet fields, which is basically just an optimization, which you can say if you only need some of the values in your edge triplet, you can have it only materialize those. Okay, so what does PageRank look like with that? So this is a simplified version of the actual implementation. So the first thing we do is we set up. And remember, we're going to take the strategy of storing our out degree in our edges. So what we're actually going to do is we're going to join to our out degree vertex RDD, get that, and then store 1 over that out degree in each edge. We're going to do 1 over just because we're going to multiply it by it later and make it easier for ourselves. And then set all of the vertices to 1. All right, we're going to do a loop for however many iterations we want. And we're going to do 2 things. We're going to aggregate messages, where our send message just takes that source vertex times the edge value, which we just stored was 1 over the out degree. And the merge was the sum. And then the next part is we're going to then join those rank updates back to the original graph and apply the PageRank formula. And voila, we're done. Okay, so almost. So let me give some quick tips and tricks before we end. So first, make sure to specify an active direction in real Prego algorithms. This can speed things up a lot. Specify triplet fields. If you don't need all of those fields when you're doing aggregate messages, specify it, and you can also speed things up. And always specify a partition strategy for your graph. Specifically, edge partition 2D is a great choice for this. Remember, this, like everything else Spark, works with immutable data. Use immutable data types for your vertex and edge data. Otherwise, bad things will happen, and you won't know why. Don't use this example code for anything serious. Use the actual implementations in the library. We took out things like caching and other stuff that you really want to have. OK, so here are the references for Prego, PowerGraph, and GraphX papers. You can check them out. And that's it. Thank you.
Thanks to the speaker for an insightful talk. We'll take questions here at the microphones. If you guys can step over.
So I noticed you didn't mention the vote to halt method in any of the GraphX implementations.
Right.
Does that exist, or does it just run every vertex all the time?
No, there is no vote to halt. It's all implicit.
Does that kill your performance for some algorithms?
So basically, how GraphX works in this is if you don't receive any messages and you are not implicitly activated by the change of one of your neighbors, then you don't run. So the reason for that is because looking at most of these algorithms, that's essentially what happens. And so it's just, that's their implicit way of doing it. Yep.
Hi, thanks for the talk. Are there any functional or practical changes to GraphX in recent Spark releases that would help someone who's using an older version?
No, unfortunately, GraphX. Oh.
They added checkpointing to Prego.
Yeah, I suppose. Yeah, I mean, there's been some changes, but not a whole lot. It's slow. It's definitely not as fast as a lot of the other components.
There's also graph frames.
Yes, there is.
So during each of the iterations, does that map sort of seamlessly down to some kind of group by or reduce?
Yeah.
So is it?
So it essentially maps to some joins and aggregations. Yeah. Okay. You are aggregating to combine the messages together, and then you are joining them back to the vertex RDD. It's a little bit more explicit in that final example of the for PageRank, but still that's a little bit abstract. But yeah.
Thank you.
Do you know if GraphX can handle multi-label scenarios where your vertex could have like a vector of values instead of just a scalar?
Yes.
Oh, great.
And that's used in some of the built-in libraries like personalized PageRank, for example.
Oh, cool. Thanks.
What are the differences between GraphX and GraphFrames, and is there reasons to use one or the other?
So GraphFrames is more along the, they're trying to do it more like data frames. A lot of the more classic, like our examples, they're really just wrappers for the GraphX implementations that could change later. They do add some cool stuff on top of it, like pattern matching. That's really cool that don't really have an easy way to do in GraphX. I don't know. It's really got to depend on your use case, I guess. Yeah. Yeah.
OK, well, thanks again.